I got a Denon SA3900. This is an integrated amp that was shipped in. And the owner asked me to check it out and see if I could improve anything on it. So we're going to do some measurements. We'll change some caps in it in the power amp. And then we'll take a look and see on the scope whether we made any improvement. Let's check it out. Today we're going to look at a Denon SA3900. This is an integrated amplifier from Denon. As you can see, cosmetically, this unit is in really good condition. Like, there's no scratches on it. This is beautiful. Even the cabinet is in good shape. You know, no serious damage at all. I'm going to open this one up before I plug it in, and we'll check this one over and see what we need to do to restore this one. Like the other one, this came from the same guy that owned the tuner. He sent them both in as a set to be serviced. So there's a look down the top of this one. If you're wondering how the capacitors are, these are 6800 microfarad at 50 volt. The main filters. $76.94 for one, and the other one $84.83. So capacitors are charging up to higher than their rated value. I can do this because this hasn't been plugged in months or weeks anyway, so I'm not going to get a shock. Main filter caps are good. Some of these little signal caps here, we may want to change them out. There's not many. We may want to change them out on here just for good measure, just because the unit is old. But it's probably not even necessary. But let's turn this thing on. We'll plug it in, hook it up to some speakers. Now I know this is probably going to disappoint some people who think that this is a big power amplifier. This amplifier is probably 30 or maybe 40 watts per channel. It's not a real high power amplifier, despite what some people might think about vintage equipment. Not everything was high power. Oh, might help if I plug in the power cord. Okay, let's see what happens here. I'm on auxiliary input, and I don't hear anything wrong with this thing. I don't even hear any noise in the controls. This has got maybe 20 watts per channel. You can hear the distortion there kicking in, and these power meters are only going up to 20 watts. We can measure the voltage on the power supply and watch when it starts to sag. I'll turn it off to connect this up. Okay, power. We'll measure the actual power across the entire load. So 67 volts is all this thing's got. And that's total. So, you know, about 33 volts per positive and 33 volts negative. But you can see the voltage starts to drop. Because this is not a high power unit. I'm going to revise my thoughts on this. 20 watts per channel, maybe 25. That's easy enough to figure out too. All I gotta do is look at the output transistors and see what they're rated. They're mounted to this heatsink, but they're mounted on the back side. Let's put the scope on it and see what we're getting as far as voltage goes before it starts to clip. So what I'm going to do is I've got a tone on here now. I'm going to turn off the speakers first of all. I've got 50 watt, 8 ohm dummy load resistors. I'm going to monitor the voltage here. This is the DC voltage. We're going to look at it on the scope, and I'm going to increase the power until it starts to clip, and then we'll measure the output and see whether we're getting the power. I'm going to drive both channels, so I got both channels driven, as you can hear. Both channels are driven. When I switch over to the B speakers, okay, now the load is now going directly to the load resistors. We're going to measure this on the scope, and I'm going to increase the volume to the point where it's going to clip, or just start to clip. And that will give me, okay, there we're starting to get into clipping now. You'll see the voltage has already dropped. Right, we started out at 66 volts. The power supply voltage is starting to drop, and if we look at the scope, I'll show you the scope as I increase the voltage or increase the power here. But where it starts to clip, right there, my power meters are showing, one showing 15 watts and the other showing 20. Could be the meters are just not quite accurate, or one channel could be higher than the other. But let's take a look at the scope and we'll see exactly what's happening. Okay, let's crank this up. The point where the distortion starts, there's where the distortion starts, right there. We'll take a snapshot of this. That way I can shut the amp off because I don't need to burn my resistors up. So now we've got a snapshot. 47.6 volts peak to peak is what we've got just before clipping. A little bit of switching noise here. You can see this. There's some distortion in here right there. Gonna test the other channel and see where it clips at. So this one was 47.6. The other channel, yeah, it's about the same. It's about the same too. 47.6 is the both of them clip at the same. So the meters aren't exactly accurate, but they both clip at 47.6. The detent slipped up a bit here. It's actually showing 48.2, but we're into clipping. 47.6 was where it went before it clipped. We'll go back and do that again. Okay. Yeah, there it is. Just below clipping is right there. Exactly the same as the other channel. So the amplifier is balanced. The 2 watt meters are slightly off. We can certainly calibrate that, but we get about 47 volts clean at 400 hertz before this thing goes into clipping. In the top here there are 2 trimmers, and if I want these to show 40 watts when it's going to clip, because that's what the amplifier is rated at, I can turn the amp up to 40 watts and just to the point where it's starting to clip, and then I can set both meters so that they both sit right on 40 watts. I could make them say anything I wanted. I could make them say 100 if I wanted, but this is a 40 watt amplifier, so I'm going to set the meters so that when it just hits that point of clipping, we're going to calibrate the meter so that they both register 40 watts. So here's one. Turn this thing up. So there's the point where it's just starting to clip. And I'll turn that meter just to 40 watts. And I'll do the same for the other one. So now they both read exactly the same. If I turn it down to 10, they're both going to read 10. As you can see, if I put my tone at 1 watt, we're looking at a watt on both meters. 10 watts, we're at 10 watts on both meters. So the meters are now tracking. Down at 100 hertz, we get the same power before it goes into clipping. We'll test it again at, we'll go to a higher frequency. I can change this thing. We'll take it up to a kilohertz this time. So this is 1 kilohertz. Let me just reset the meter here, or reset the scope. You see where 1 kilohertz starts to clip. There's 1 kilohertz. So same thing, same voltage. We've seen that same little bit of distortion. And that little bit of distortion is on both channels. That might be the generator. I had the signal level turned down. Let me just adjust my signal meter here. I had my generator attenuated. That's looking a little better. That distortion that I was seeing is gone. That must have been coming from the generator because the level was turned down. That's 1 kilohertz. Let's go up to, we'll go up to 5 kilohertz. See how it looks on 5 kilohertz. Five kilohertz, we're seeing a little bit of distortion here as we get up to full power. Again, it's going to peak out at the same voltage. We'll take this up now to, we'll go to 10 kilohertz this time. At 10 kilohertz. Now, you see the amplifier is really starting to distort. I'm going to give myself some gain and not bother to drive this thing quite as hard. But as you can see, we still clip, but it's the waveform is no longer a sine wave when we get up to 10 kilohertz. And my signal coming off of the meter, off of the generator, will be a sine wave. But it's certainly certainly not as clean as it was on the lower frequencies, that's for sure. It's actually quite nasty as we get into the higher frequencies. I can take it higher than that too. Let's go to we'll go to 15 kilohertz. And see how ugly 15 kilohertz looks. We're putting about 3 watts out now. Doesn't look at all like a sine wave. probably go back down to a more reasonable 5 kilohertz. Even 5 kilohertz, we're seeing some crossover distortion. One kilohertz. Actually hearing it sing through the resistors. Probably got those resistors red hot at this point. And back down to my 400 hertz, which is normally where these amps are tested. Everybody uses 400 because, you know, they should be able to handle 400 hertz, see, nice and clean at full power. Anyway, that's just a little bit of an experiment here with this thing. I can kick both speakers on at the same time, then we can see the scope. This unit may benefit slightly from changing out a couple of these caps, the coupling caps in the amplifier board itself. They all look to be pretty good quality caps. These ones down here, obviously these are in the phono preamp. The ones over here, these are the tone control in the tone control circuit. These ones here are coupling to the power amp. So it may benefit from changing these caps, so maybe we'll do that since it's here anyway, and I've got some. We'll look at the measurements again once I change them. So to change them out, I just have to remove the amplifier board itself. Okay, so this amp board will lift out. Then I can work on. Then I can separate this board. There's two more screws that hold the preamp board to the heatsink, and the output transistors are connected in behind here. We can take this one, take the shield off. I've already discharged the capacitors, by the way, when I unplugged it, so not to worry about that. I'm thinking we'll change these caps here. These are going to have the most influence on the sound itself, because all of the signals, all the audio signals for the left and the right channel, one's for left and one's for right, but everything goes through these. These are the coupling caps that couple the preamp to the power amp, the power outputs, which of course are, the power outputs are back here. See, these ones here, B617 and D587. These are Class B, basically. It's a push-pull, but it's biased as a Class AB. Anyway, let's change out these caps and see whether there's any noticeable change in the sound. I'm not expecting any, but what the heck. I'll actually measure this when I take it out too and see how it looks. We'll measure the ESR and we'll measure the capacitance of this one. This is a 100 microfarad at 50 volts. So there's the old one. Negative is this way. marked on the board here. Positive and negative, it is marked. Well, let's just measure this first of all and see whether it's close to 50 or close to 100. So it's measuring 120 microfarads. The new one, $102. A little more modern caps are a little more accurate than the old ones. The old ones could be way off. Usually they were higher. This one here, the other one is 101. So they're going to be pretty much balanced. We'll look at the ESR characteristics of the old one versus the new ones. It shouldn't make much difference, you know, in terms of the sound quality either, but at least that's one thing can be said about new capacitors, is that the tolerances are much better on them now than they used to be. Although the reliability might not be as good. But yeah, 0.7? No, 0.1. So 0.18, 0.2 call it, for 100 microfarad at 50 volts. It should be like 0.3 is, so it's you know, well, there it is, 0.3. How's the new one look? 0.2. So ESR wise, these ones look to be about the same. 0.2. So spec wise, the new caps look to be, other than the fact that they're a little closer to their rated size capacity, otherwise they look the same. Next we'll do this other little one here. This one is .22 at 16. So we'll just see whether this one's close. 31. They're all probably going to be a little higher, I would think. How's the ESR on this one? .5. So 22 at 16. Yeah, see, it's still well within spec. 22 at 16, 3.6. This one's 1.5. I think these caps are fine, but we'll change them out anyway. We'll change them. We'll change out these ones. We just change out this other 100 while I'm thinking of it, and then we'll do the 22s. The 22 microfarad, the ESR is actually lower on the new one because the other ones were measuring 1.5. This was measuring was it 0.6? So these ones here, actually the ESR is lower. And capacity wise, 26. We're good. We're good. The other one is these other two little ones right here, which is this one's a 1 at 50, and then there's one more to do as well. The 1 at 50 coming out of it, 4.3 is the ESR. The new one's going to be a little lower than that, 2.9. Guess I gotta clear the holes of solder. And the last one down here is another 100 microfarad at I think it's 25 volts. One more down here. A TOA 100 at 25. See how far off or how close these ones are to their ratings. 125. Those are pretty close. Thermal compensator, got to bring it back down here so it's touching against the back of the heatsink here. It's held in place with a clip. Got to put the clips back on. So these are the thermal compensation diodes, and basically what they do is they're held onto the heatsink by these copper clips. Copper clips just pop in like that. Well, they're supposed to. They hold these up against the heatsink, so that the heat transfers into the diode itself, and what that does is it will change the voltage drop based on the temperature of the heatsink. So as the heatsink gets hotter, it will change the conduction or the drop of the voltage across the silicon diode, which will dynamically adjust the bias for the transistors as they heat up to compensate for the junction in the output transistors themselves. Because if they get too hot, what will happen is there'll be internal resistance will change. You will get leakage, internal leakage across the junction. And if it's not controlled by turning down the bias, then what will happen is it will continue to get hotter and hotter, and of course as it gets hotter, the thermal or the voltage drop will change will drop, which will cause more current, which will of course allow the thing to get hotter. The device will get hotter again, and eventually you'll end up in what's called a thermal runaway condition, where the transistor will basically commit suicide. It'll start feeding itself its own bias voltage through leakage between the base and the emitter. So what happens is as the temperature rises, these diodes here, which are clipped onto the heatsink right here, they will adjust the bias to cut the current back to the transistor to stop it from getting into a thermal runaway condition. And that's just a bias compensation. There are other technologies that were used in amplifiers. Techniques called it New Class A. Sony called it legato linear. And that's completely different. This is just a static dynamic bias, basically. That's thermal compensation. The legato linear and the New Class A, as techniques called it, was actually a dynamic bias which changed the bias under low signal levels. So when you were playing music very low, they would actually throw a heavy bias onto the transistors to keep them from going into cutoff and basically make the amplifier operate as a Class A. This doesn't do any of that. This is just a thermal compensation is all this is. Not to confuse people with some of the other technologies that more modern amplifiers used. This is just a basically a Class B amplifier that's biased as a Class AB. And that's what those diodes, those thermal compensation diodes do. They keep the amplifier, keep the temperature in check so that we don't have it going into a thermal runaway. Okay, looks like we should be able to power this amp again and see if it sounds any different now that it's got new caps. So, power on. And... well, it's to my ears, it sounds about the same. I wasn't expecting any, any huge differences. Subtle, maybe. The treble sounds like it might be a little bit brighter when I turn up the treble control a bit, but you might wonder why I didn't change this cap over here. This is a power supply, I believe, but this looks like it's been replaced. This is a newer cap, so somebody's changed that one at some point. It's green. But anyway, I've changed the caps in the preamp on that, and I think that's about where I'm gonna stop on this one, because I don't think it needs anything more. The old caps measured fine that were coming out, so it's got new caps in it. We're gonna leave it at that. I'll measure that power level again and see how the signal looks. See if it's any cleaner. Okay, let's see what we get before we go into distortion. Remember we were at 47.6 volts before. Let's see if we get any more juice out of this thing now. Okay, looks like we're creeping up to 50 volts now. So 51 volts peak to peak before we get into clipping. So hey, we've sneaked a few more watts out of this thing, because before it was clipping right here. It was clipping at like 47 volts. So we have made a slight difference. We've gotten a little bit more power out of this thing just by changing those tired caps. I bet you we're getting the full 40 watts out of it now. So here's 10 kilohertz with the new caps. Okay. And we'll try 15 kilohertz as well. So that's 10 kilohertz. And this is 15. Looking a lot better than it was before. Okay, still a little bit distorted there, but I think it's looking, I think the waveform's looking a little better with the new caps. That's 20 kilohertz. And down to 1 kilohertz. Looking good. Looking very good. So there you have it. Changing out these older capacitors in here has increased the power output a little bit. And, ow, yeah, hot. I only ran that thing for a few minutes, and these power resistors, which are rated at 50 watts, are actually quite toasty. So that's it. Thanks for watching. We're all done on this one. I'll switch this back to music. Guy who owns this will be happy to get it back, and it's got a refreshed sound. As I say, I think that the highs sound a little cleaner. So there you go. That's a Denon SA3900 recapped, sounding great. Thanks for watching.